Hello, my name is Sony Kapadia, and today I'm going to be giving a brief presentation on crystal synthesis and a specific project we've been working on in the Chan lab. Crystal growth is an extremely important area of research that involves many intricate steps for satisfactory results. Due to the time and effort needed, one might be inclined to ask why crystal growth is done in the first place. When we look at the world, many times we take the conveniences we have for granted. But the truth of the matter is that these conveniences wouldn't exist if it wasn't for the foundational materials that they are built with. This brings me to the conclusion that crystal growth is primarily done in order to isolate specific properties of different materials that have crystalline structures in order to make future innovations that are desired. In the lab, I worked with intermetallic phases, but different labs can investigate different crystals to isolate properties. The full crystal synthesis process starts with stoichiometry, which is used to determine how much of each element needs to be massed in order to produce the desired phase. Then these reagents are arc melted in order to remove impurities and create a homogeneous mixture if multiple reactions need to be run with the same ratio. Arc melting can be skipped if powder is used when weighing out the elements because powder cannot be arc melted. Next, the measured reagents and the flux are put into a crucible, which is then put into a silica tube and fused in order to prevent the incorporation of oxygen into the desired intermetallic phase. To elaborate, a flux is the element that the reagents are dissolved into in order to create a supersaturated solution. This mixture in the crucible is then put into a furnace where the flux is melted and the reagents dissolve into the flux to create the supersaturated solution. This melt is then slow cooled until the crystals composed of the reagents in the crucible are formed, and then the silica tube is taken out and centrifuged before the melting point of the flux in order to remove the flux. Sometimes all the flux does not come out when centrifuging, therefore the crystals need to be etched before more analysis is done. After the crystals are taken out of the crucible, a method of analysis known as X-ray diffraction is performed on the crystals. To elaborate, first, before complex analysis is done, one must run powder diffraction on the crystals formed. This is where one crushes a sample of the crystals into a powder and puts it in an instrument that determines all the diffraction directions of the lattice. These diffractions are converted into a graph that show peaks of max constructive interference. This graph can be cross-referenced with graphs in a database in order to determine what one has formed in the experiment. If a desired crystal phase was formed in the experiment, one can move on to single crystal diffraction. In this process, a single crystal of the sample is taken and put into an instrument that gives an area of electron densities. These densities can be used to determine the positions of atoms in the crystal. Many people may be confused when I'm referring to X-ray diffraction, so let me explain what exactly it is. X-ray diffraction is when X-rays are fired upon a crystal and the X-rays diffract into a pattern. This is done with a rotating arm that fires X-rays at different angles to get points of max constructive interference. There are two main types of X-ray diffraction, powder and single crystal. In powder diffraction, the crystal sample is ground into a powder and X-rays are fired upon it. For single crystal, the X-rays are fired upon layers of atoms, and the atoms diffract the X-rays in a way that they're either constructively or destructively interfered with. When the crystal that was synthesized is known, it is tested for properties that include magnetism, conductivity, and others based on the reason why it was being synthesized. These crystals can be used in different things based on their respective properties. Critics of crystal growth may ask why one would ever invest so much time and effort into creating pretty rocks, but when one looks at the future implications of crystals, the answer is obvious. As the world progresses, new innovations must be made in order to continue advancing the quality of life of everyone, and crystals are one of the building blocks to these future innovations. An example of a new discovery that was made in the solid-state field is topological insulators, which are insulators on the inside but conductors on the outside. This has a plethora of applications in the electronics field when it comes to making wires safer and cheaper. In the time I have worked in the Chan lab, I played a role in the synthesis process of many different crystals. However, the primary project throughout the research experience was the 5413 project. These numbers refer to the Ce5, CO4, Ge13 phase and represent the ratios of each of the elements. As seen in the table, many different variables were changed in order to attempt to get the desired 5413 phase, and these included the ratios of the reagents, the heating profiles, and the fluxes that were used. The general results of the experiments are seen on the right side of the table, but I will go more in depth about the specific findings associated with the experiments. To begin, it was determined that arc melting the reagents before putting them in the furnace forms the more stable 1,1,3 phase instead of the desired 5,4,13 phase. Also, it was determined that centrifuging temperature doesn't matter as long as it's below 815 degrees. In conclusion, crystal growth is an extremely important area of research that allows for future advancements to be made. I would like to give a special thanks to both Ashley and Justin for taking the time to teach me about the intricacies of crystal growth, Daniel for allowing me to help him on his projects and teaching me that research can also be fun, Abby for lighting up the office with her personality, and finally Dr. Chen for taking me in as an intern and giving me the great opportunity to expand my views in chemistry and physics.